In this video, we are going to learn how to simplify a product of radical expressions. Now, if you have two radicals that are being multiplied, as long as their indexes match, they can be combined into one radical. Another condition is very important because we're going to talk about it in the following examples, is that a and b must be real numbers for this property to apply. Now, for every one of these examples, we're going to multiply if possible, then we'll simplify it, and then use absolute value symbols when needed. And that when needed is going to be a key word in these examples coming up. So we'll start with the first example, the cube root of 6 times the square root of 2. Now I just mentioned that the indexes need to match, and here I have a third degree index and then a second degree index, so that their indexes do not match. So this is not possible to multiply. So that would be as simple as that expression actually gets. It's just the cube root of 6 times the square root of 2. But now over here we have the cube root of the cube root of negative 4 times the cube root of 2. Now, do you need to be real numbers? The expressions, I think I might have said a and b earlier, but the entire expression needs to be a real number for them to multiply. Now, luckily, the cube roots can have negatives in them. That's okay. That won't yield to an imaginary number, so this is fine to multiply because the indexes match and they're real numbers. So now I can combine them into one radical. So that's the cube root of negative 4 times 2, which is negative 8. And what is the cube root of negative 8? Well, 8 is 2 cubed, so this becomes negative 2. And in case you don't remember that power, I could rewrite this as negative 2 cubed. Now over here we have the fourth root of 7 times the fifth root of 7, and sometimes what's underneath the radical, the radicand, will match, but since the indexes do not match, this again is not possible. Now for this next example, I have the fifth root of negative 5 and the fifth root of negative 2. Again, odd roots, but they have negative numbers, so they both are real, and their indexes match, so this becomes the fifth root of negative 5 times negative 2, which is 10. And now, is there any number to the fifth power that can make 10? No. Now you may be thinking like 2 times 5, but that's not 2 to the fifth power, nor is it 5 to the fifth power. So this is as simplified as it gets. Over here, the square root of negative 4 times the square root of negative 9. Now the indexes match, but the square root of negative 4 and the square root of negative 9 are not real numbers. So I can't use this property. I actually have to simplify it before I can actually multiply them. And all it means to do that is just to, this square root of a negative number is I. So I'd have to make this I square roots of 4 times I square roots of 9. And then in this way, now that I'll have I squared, square roots of 4 times the square roots of 9, that's something I can multiply. Because the square root of 4 and the square root of 9 are real numbers. Leaving me with I squared times the square root of 36, which will be negative 1, which is what I squared is equal to, times the square root of 36, which is 6, leaving me with negative 6. But the big mistake you can make, I'll even label it here just so you see it, is sometimes you won't think about the real number approach. And if you were to multiply these, negative 4 times negative 9 is positive 36. And you may end up getting an answer which is positive 6, which would be incorrect. That's why you need to keep in mind they need to be real numbers for this to work. And lastly, we'll have the cube root of 4 times the cube root of 6, which I can combine. They give me the cube roots of 24. Now I'm looking for perfect cubes inside of 24. Now, it's not a perfect cube itself like you saw with this upper example, so I need to actually think of its prime factorization. A good way to find the prime factorization of any number is to make a factor tree. We know that 24 is 4 times 6, 4 can be 2 times 2, and 6 can be 2 times 3, And these numbers that you get at the very end where you can't split up anymore is known as the prime factorization of that number. So for 24, its prime factorization would be 2 to the third times 3 to the first. And rewriting 24 in this way can help you see how to simplify it a little bit easier. Because now I have the cube root of 2 to the third, which is just 2. And then the cube root of 3, which doesn't simplify, leaving me with 2 cube roots of 3. Now let's look at this with variables. Now, there's absolute value symbols when needed. We are dealing with the square roots being multiplied. So usually absolute values will be used, but we'll see here that x is being raised to a third power and the first power, which means x could be positive or negative, but since taking the square root of an imaginary number would not allow us to combine these, we're going to assume that the values we get for x will be positive, because otherwise it'll be non-real. Over here, we see have y squared, which is always going to make that term positive, so y maybe could be negative, but the fact that the other square root is y to the third, that means it could be negative, so we're also going to assume that y is greater than 0. So we don't need to worry about absolute value symbols anymore, since we're assuming that x and y will be greater than or equal to 0. So now when I combine these, they do have a similar index, and now we're forcing them to be real numbers so we can combine them. That gives me the square root of 772 times 10, which is 720, and then x to the third times x, which would be x to the fourth, and y to the second times y to the third, which would be y to the fifth. And again, I want to look at the prime factorization of 72 so I can see which perfect squares are within 72. Now, within 720 can be split up into 72 times 10, just like we saw. 72 can be 8 and 9. 8 could be 2 and 4. That 4 could be 2 and 2, going back up. 9 could be 3 and 3. And since I'm having a lot of numbers, I'm going to start circling all my prime numbers so I don't lose track of them. And 10 could be 2 and 5. So 720 can be rewritten as 1, 2, 3, 4 2s, so 2 to the fourth, times 2 3s, so 3 squared, times 5, times x to the fourth, times y to the fifth. And now we will simplify. We do not need to use absolute value symbols since we're already assuming x and y will be positive. So the square root of 2 to the fourth, we'll do that in understood 2. So 4 divided by 2 is 2 squared. 2 divided by 2 would give me 1, so 3 to the first. 5 doesn't have a power. It will remain within the square root, so I'll put the square root over here. And it has a 5 in it still. And then we have 4 divided by 2 leaves me with x squared. And this 5 divided by 2, 2 goes into 5 twice, but with a remainder of 1. So I can leave that remainder of one of the y's on the inside of the radical, since it didn't completely come out. Only y to the fourth came out of here. Simplifying this, we have 2 squared times 3, which would be 4 times 3, which is 12. X squared, y squared, times the square root of 5y. And again, really think about these radicals as like a way of dividing these powers. The remainders stay on the inside of the radical, while all like the whole numbers that can go into it come to the outside of the radical. And you just kind of go term by term. Now, another way you can approach these problems, again, you'll see another similar pattern here. It's a fourth root, but x to the third and x to the fifth could be negative. So I need to make sure that x is absolutely positive here for us to be able to combine these. Even taking x out, sometimes you have to assume that's positive since it could lead to an imaginary number. That y by itself could be negative, so we have to assume y is also greater than or equal to 0. So again, we won't need to use the absolute value symbols since we're already assuming that those two variables are positive. But one thing we can do before we multiply is actually find the prime factorizations of 81 and 32 before we start, so we don't have to do it with a bigger number. So 81 can be written as 9 times 9, and each of those 9s can be written as 3 times 3. So the prime factorization of 81 is 3 to the 4th. So I have 3 to the 4th, the 4th root of 3 to the 4th, times x to the 5th, times y to the 4th, times the 4th root of 32, which can be written as 4 times 8. That 4 can be written as 2 times 2. The 8 can be written as 2 times 4. And that 4 from there can be written as 2 times 2, leaving me with 5 of these 2's. So 32 can be written as 2 to the 5th. Then we have x to the 3rd and y. And now when we multiply them, we can multiply numbers with similar bases. So this 3 and this 2 don't have a similar base. So when they combine, I just write it as 2 to the 5th times 3 to the 4th. And then we have x to the 5th times x to the 3rd, which would be x to the 8th. And y to the 4th times y, give you y to the 5th. So when I go to simplify, I'll have the 4th root of 2 to the 5th. So 5 divided by 4. 4 goes into 5 once, so 2 to the 1 power comes out. But what remains inside of the 4th root is that remaining power of 1, the remainder. So 2 to the 1st. 4 goes into 4 once, so 3 to the 1st comes out. 4 goes into 8 twice, so x squared comes out. And 4 goes into 5 once, but there is a remainder of 1, so 1 of the y stays in. Leaving me with 2 times 3, which is 6, x squared y times the 4th root of 2y. And that is how you simplify a product of radical expressions.